Thank you. Let's go back to August 2nd, 2014. As residents of Toledo, Ohio, awoke to an urgent warning not to drink or use their tap water. Due to high levels of toxic microcystin produced by algae bloom forming on the surface of Lake Erie, 500,000 of people in Toledo were unable to use their tap water for 3 days. This situation can happen anywhere, and it will get only worse in the future with global warming. Warmer water temperatures are fueling harmful algal bloom, such as the one in Toledo and the recent bloom off the Florida coast back in 2018, where thousands of fish died and both tourism and the local economy were impacted. These incidents can happen without warning. So what can we do to get in front of these events, or even know these events could potentially happen? Consistent water quality monitoring is the most common approach, but traditional water quality monitoring is time-consuming and labor-intensive. It usually comes with high labor, equipment, and operational cost. And unfortunately, with all these methods, we're not able to develop a holistic view of water quality in our water bodies, which makes it difficult for us to make critical decisions in real time. Remote sensing is another alternative method to monitor water quality. As you compare these two diagrams, remote sensing can provide a holistic view of water quality in our water bodies, and it can also reduce costs and time commitment by processing thousands of samples across the entire water body in less time and with far less labor. Remote sensing, therefore, is a valuable alternative compared to traditional water quality monitoring. But how does remote sensing work? It works by using satellite imagery to monitor important water quality parameters. Parameters such as total suspended solids, sea surface temperature, nitrogen, phosphorus, and chlorophyll A. And how does satellite-based approach work? Features on the Earth can emit, transmit, absorb, or reflect electromagnetic energy from the sun. Sensors have been developed on board of satellites to capture this electromagnetic energy. These sensors allow us to monitor different water quality parameters and monitor features and changes on the Earth. But one of the challenges in monitoring water quality using satellite images is finding a method to identify a relationship between collected water samples and satellite imagery. This relationship is usually very complex and nonlinear. And our previous studies show that machine learning algorithm can be a valuable tool to capture these nonlinear relationships. Because not all sensors on board of satellites are the same, we have multiple different choices of sensors to monitor different water quality parameters. This graphic shows the many of different choices of sensors available for each different water quality parameter. Choosing the right sensor is one of the most important steps in monitoring water quality using satellite imagery. And this selection depends on the type of water quality, type of water body, and amount of pollution being monitored. It also depends on spatial and temporal resolution of available satellite imagery. Satellites with higher spatial resolution images can provide more reliable data for monitoring water quality. But these satellites are usually expensive and they come with lower temporal resolution. Therefore, choosing the right sensor has always come with a trade-off between a spatial and temporal resolution. With our technique, our clients will no longer need to choose. We can provide both spatial, high spatial, and temporal resolution data at the same time. So some satellites can pass this study area more frequently, but their images are fuzzy. Then we have other satellites that they can actually pass our study area They can provide less fuzzy images, but they can only pass the area every 10 to 14 days, which cause a huge gap in satellite imagery and the resulting monitoring data. Our method is based on data fusion. This means that we use comparisons of a pair or multiple pairs of satellite collected on the same day and extract the best features from both satellites to generate higher spatial resolution imagery. So instead of having those fuzzy images with limited data, we will be able to provide higher spatial resolution images with the data that we need every single day. So let's look at this process in practice. We have applied this technique at Lake Mead, which is located on a border of Arizona and Nevada. This lake helps supply water for 25 million people, and it's the largest reservoir in US by volume, stretching 180 kilometers with a total capacity of 34 billion cubic meter. Because of the scale of this lake, client required a near real-time monitoring system to see the impacts of transported sediments from Colorado River, transported urban runoff from Las Vegas, and the impacts of forest fire events around the lake. Since 2000, water levels have continued to drop about 48 meters. And this year, the lake was only 27% full, which is the lowest level it has ever been since it was filled back in 1937. Reduced water levels lead to increase in concentration of contaminants in a lake and elevates the need for having a near real-time monitoring system. And our technique can do this reliably. Here's an example of applying this technique at Lake Mead. The first two rows from the top show the available satellite images. The third row shows fused images generated by our technique. These images were applied as inputs into machine learning algorithm to produce total suspended solid concentration map, which show at the last row. We can use the same process to generate concentration maps for any other water quality parameters. To help visualize and interpret the results for the client, we also develop a user-friendly interface. At Stantec, we call this service WaterWATCH. WaterWATCH can provide historical record of water quality. It shows trends both seasonally and year over year. It provides early warning system at near real time, and it detects pollution sources. This means that WaterWATCH can help safeguard our water sources. That concludes my presentation. I'll be happy to take your questions. Thank you.